Today we're learning about inclusion. Okay, actually, we're learning about DP. It's not actually. All right. Well, let's just like look at a problem. Here we go. So I'll give you. Yeah, this is the problem. You have a binary. You want to count the number of binary strings of length n. It's just that no substring. You have no more than k ones in a row.
Can I request dark mode for the recording?
Can I request dark mode for my eyes?
You can request lots of things.
Okay.
It's harder to read. Can we turn off the lights?
Yeah.
Actually, that might
Thanks,
be an
Saga.
issue.
Much.
Can I request high contrast mode?
I'm sorry.
Actually, that's a lot
amazing.
better. Do it like that.
This is
Alright,
fantastic.
no sleeping.
All right.
Huh?
Does anybody solve the problem yet?
So brave.
Okay.
Inclusion-Exclusion.
Okay. No.
Sorry, DP.
Okay. But like, what do you mean by that?
Count the number of binary strings of length n with no more than k ones in a row.
Count the number of binary strings that do have k or more ones in a row.
Okay. How are you gonna do that?
TP.
Okay. Well, I mean, like you could do that, but also like you could just not do that. All right.
Well, now you just like you do O of n times k, right? But if you
Can you elaborate on that?
like you store which index you're on and how many ones you have in a row so far.
Okay.
That's too slow.
That's too slow. Yeah.
I think you can speed it up by doing some prefix sums.
Okay. This is some good ideas. But I'll show you something. Check this out. So we're gonna do a DP, and it's gonna go like this. And it's like. Okay. Let me.
Do you want to make the size n plus
I
one?
was gonna say.
I think it should be k.
Should be K,
Yes.
but it's a bit tricky here. Okay. So what do you guys think about this?
That's a DP.
Does it work?
It's a DP.
What is he doing?
Was there any questions?
does that work?
It's like saying your next letter can be either a 0 or a 1, but now you want to remove from this like count the number of ways to make like the length I minus k string before it and then add on a bunch of ones to it.
Yeah. Okay.
Question about the problem. Is it specifically you can't have more than k ones, or you can't have k of the same
K
digit?
ones.
Okay.
Oh, yeah, because you see the first example. I forgot to go over the examples, but 11000 is valid.
Oh.
It's a good string. Now, like, I don't really know where it's going with this, but does anybody like, is anybody confused about this? Okay, Quinn.
Yeah, what is the DP actually trying to store? The answer?
It stores like the answer, like for every prefix of length, like for every length, DP of I stores the number, it should store the number of strings of length I that satisfy this property. Okay, Tyler?
And then the transition is saying there's two, like, we can either take a 0 or a 1.
Mhm.
But if we take a 1, then if we took k1s, we have to exclude all strings with k less characters.
Yeah.
Alright.
So, okay, let me like write out some examples, I guess. Like, so let's say we have a valid, let's say k equals 2, and we have some valid answer for k equals 4. We can always like, if we have a valid answer for k equals 4, we can always try to like add a 0. If we add a 0 to it, it's always gonna be fine. And then, this marker does not work. 0, 1, then we can turn this into 0, 1, 0, 1, 0, or we can turn this into 0, 1, 0, 1, 1. So for any valid string of length k minus, or of length I minus 1, we can always just like add a 0 or 1. So that's where we get this times 2 from. But now this is going to be bad if we have a case like where our previous string is like already has k ones at the end. So if you have something like 0, 0, 1, 1, that has 2 ones at the end. So if you try to like add a 1 to this, that's not going to work. So we have to like remove these. Does that make sense?
So you're like including the both options, excluding the bad.
Yeah. So now, so okay, this DP doesn't actually work though. There's a problem with it. Cause I guess this should be less than or equal to k plus 1, and we want to subtract out k plus 1. Because it's gonna be bad, it's like bad if we have, wait, should it be k plus 2? I don't know. We want to subtract out the cases where we have a suffix of k plus 1 ones in a row. Right, so here if we're like at n equals 5, then we want to subtract out the cases where this prefix of length 2, like we just want to subtract out all the ways that this prefix of length 2 works, and then we added k plus 1 ones at the end.
So is the problem at most k consecutive ones are in the string?
Yeah.
Okay, that makes sense.
Oh,
now.
But there's like, this is still not right. Okay.
Can't you also just add 1 to k? And then like, make it the other problem?
Randy?
So like, are you saying it's like k plus 2 because you have to force k plus 1 things to be 1 and then you have to force 1 thing to be 0?
Yeah,
Okay.
exactly. Actually, what do you think about that? No. Wait. Okay, Brian G.
Okay, well, let's say we have like 0, 1 as like a working 2 prefix, and then we add on like 1, 1, 0 after that, and k is 2. Like that's 3 ones in a row, but that's not getting like excluded there.
Yeah, you see, but then this prefix of length 4 doesn't work, right? So that wouldn't have been counted for the,
Oh, okay.
yeah, this wouldn't have been counted in VP of I minus 1. So, okay, I guess what we're really trying to count is we're really trying to like exclude the cases that work for, so okay, we're trying to exclude the cases that work for DP of I minus 1, but don't, like the prefix of length I minus 1 works, but the prefix for length I doesn't work. And the only way this can happen is if you have exactly k1s at the end, right? So if you have like, let's say, for example, you have 2 1s at the end, this is like, you have to have exactly 2 1s at the end. Because if you have more than 2 1s at the end, like if you have 0, 1, 1, 1, then this is already bad for I minus 1. You wouldn't have counted this. And if you have less than 1, 1 at the end, then this is like, it doesn't matter what you add on to this because now it's like, it's fine. Yeah. So that means that we have to force the last k plus 1 characters. Because we have to force the last k characters to be 1s, and then we have to force the character before that to be a 0. So that's why so yeah, this should be k plus 2. So,
You're like actually forcing the last k plus 1 characters to be 1s, though, aren't you?
no, the k plus 1 character should be a 0.
Yeah, no, like in the thing you're subtracting, you're assuming the character you're adding is a 1.
Yeah.
And then those
Okay.
k mod 1s. So
Yeah, you're right,
k
you're
plus
right.
1 1s.
He'll put 1 to 0.
But then
But
we
you
also
also
want
want
to
to
go
zero
to the
before
index
that.
before that.
Plus 2.
Yeah.
So it's k plus 2.
So like, okay, you're right. If you, the last k plus 2th characters from the end of the I prefix are forced. We force k plus 1 ones at the end, and then the 0 before that to be a 0. All right. And there's like one more problem with this. I wonder if anybody can see it. Tyler?
Shouldn't the, oh, never mind.
Could it be up there? I haven't actually like tested this. I don't actually know what the correct answer is, but okay. All right. So this breaks when you have n is equal to k plus 1, right? Because you can have all 1s, and this is not going to count it because like k plus 1 is not greater than or equal to k plus 2. So I guess we just have to like say if I is equal to k plus 1, then you can just like, yeah, it should be good. All ones, k plus, like, when I equals k plus 1, all ones is bad.
Yeah.
But you don't have like a character before that to fix. Like you can't force the character before that to be 0.
Shouldn't that be dp of I minus equals dp of I minus 1?
No, because the only bad case here is
Oh,
the
yeah.
case where they're all ones. Right, something?
So you're using k plus 2 because you want to only include the last bad occurrence.
Yeah.
Because it's as if this k plus 2 thing was a 1, then there would be occurrence before.
Yeah, exactly. All right. You know what? Let's run it. Let's make sure it works. Oh. Yeah, seems about right.
Is the problem that you have linked to exactly this problem?
Okay, yeah, that's a good question. So this problem is like a more, you know what, let's start going into that. Let's do some variations on this. So what if I told you that some of the characters were already fixed? What would you do? Like some of the characters are already either 0 or 1. Like I give you a string that's some question marks. It could be like 0, question mark 1, 0, something like that.
If your current character is a question mark, you do the transition we already talked about.
Okay.
If your current character is a 0, then that's never going to be problematic, so you can take your previous DP answer. And if you're a 1, you have to check to see if you can make a suffix of exactly k plus 1 ones.
Okay. So
And do the exclusion.
what do you mean by you have to check to see if you can make a suffix k plus 1 ones?
You have to check to see if every character from you to k plus 1 characters, or k characters before you, can be made a 1.
Okay.
So essentially, do you have any 0? Like if you have any 4 zeros in that, then you're guaranteed that this suffix will never be bad.
But you also have to do that when you're a question mark as well, right?
Yes.
So it's like, really another way to think about it is, you have like 2 transitions. You have the 0 transition and the 1 transition, and like if you're a question mark, you can do either. And if you're, so, if you're a 0 transition, like you get the idea, right? You just have 2 transitions and you just case out like when you hit each one. So, no. You know what? I'll code it. So, like, first of all, we want to like split this. We want to split this into 2 cases. We want to have like a 0 transition. So the 0 transition is like you just add a 0. You can always add a 0 onto like a smaller answer and it will work. Oh, also, yeah. So.
Should this only be done if the strings character is a 0 or a question mark?
Yeah, sure. Let me just. Just say if it's not equal to 1, then you can do the 0 transition. That's that. And then the rest of this is the 1 transition.
But we need to check to see when we start our last 0.
Wait, what's that? Oh,
Because if we've seen a 0 within the last k characters, then we're guaranteed that like we're never gonna have a bad suffix here.
yeah. I got.
When you're taking the ith element of the string, you have to subtract 1 from I since you're starting I equals
Wait. Where do you?
1. Like S of I should be S of I minus 1.
Oh, right. Okay, so now, so Tyler was saying we need to store the last, we need to know where the last 0 is, because if like, we have 0 here, then we don't have anything to subtract out, because like everything is going to be good no matter what. Let's just,
-1.
let's just say, if we have 0, you know
Doesn't
what?
that go at the end?
I feel like this should probably go at the end. I guess it doesn't really.
It doesn't matter because if it is 0, like you
Yeah,
want,
we're not gonna care about it.
say it's -1, but this should also be -1. And now we have to, right, so.
Shouldn't it just be like an and in the one transition part?
Yeah, that's a good point.
Don't we need to do it for both conditionals though?
Yeah, you could do actually. So if, so what exactly is this saying? We wanna know like if within the suffix of, so I guess what's the first character of this? So I is like the one, so we would just do I minus k, k plus 1, I minus k plus 1. I think that seems right, because
I think last 0 should be smaller than initially, otherwise it might trigger it here, right? I guess it might not matter.
oh, yeah, and you're saying, yeah, and I'll put this.
Parentheses are balanced.
And then.
You have an extra parenthesis on line 43.
Okay. Does this seem like do you guys think this will work?
I think this seems reasonable.
Okay, because it's not gonna work. There's one other thing we need to do. We need to make sure that the character before, like,
It's a 0.
yeah, the character
Oh,
before can
right,
be a 0, it's not a 1. So here we just say like BP or S of I minus P plus 2.
Does not equal 1.
Yeah.
Do we need an extra -1 because of I being 1 indexed? No, never mind.
Yeah, I think it's fine. Seem reasonable to everybody? Okay, I think this works.
Instead of I shouldn't be like if the last 0 is like k plus 1 distance.
K plus,
It's when you say like I equals k plus 1, it doesn't make much sense.
well, I is 1 index. I is like the length of the prefix that we care about. So then,
Yeah, but not equal to k plus 1. If the last 0 is like k plus 1 away from I.
wait, sorry. Oh, yeah, should this be a less than or equal to? Is this what you're saying? Like, this should be a less than or
No,
equal
no, no. Down there in the I. So if it's I equals k plus 1, if last 0 is k plus 1 distance away
So
from I.
that I is equal to k plus 1, that's specifically checking for the condition. If like
Oh.
you
I know,
Talking
but
about
like,
line
in this
41.
case, you need to like the last 0. If it's exactly like k plus 1 characters,
Oh.
there's only one bad transition that is
That
one.
case, it's only k plus 1 once.
Yeah, but no
There's
I,
no
it's like,
zero.
I is the wrong variable there, like I may not be equal to k plus 1, like
wait, okay, which line exactly are you talking about here?
41.
41?
I'm 42 as well.
yeah, so that's supposed to be just like one edge case that's like
I know, but
eliminated.
Are you- so are you saying
like
that-
it's literally only when I is k plus 1 where that edge case is.
Is it, are you saying like this part is the, like the
no, in 41.
41?
Yeah, I feel like it's like that edge case will also happen if like the strings.
Okay.
It's like
There's
the same edge case, but like with the question mark character.
So the reason why 41 is an edge case is because line 42 relies on us being able to force the k plus 2 character from the end of the string being 0. But we can't do that in 41 because we don't have a like character that far away. Like this is saying if our prefix is linked to k plus 1, or if the length of our string is k plus 1, there's no way we can fix a 0 because that character doesn't exist.
Okay.
So that doesn't end up working with 42.
Yeah. So, okay, let me like write out some examples. So here's like, let's say k equals 5, and then you have a case where you have like 6 ones. Here, like, then when we get into this case, we want to subtract out this case with 6 ones. So that's what line 41 is for. For line 42, or I guess it's not, it's like different now, but you get the idea. Let's say k equals, 5 again, and then let's say we have something like 0, 0, 1, 1, 2, 3, 4, 5, 6. Here it's like, we're gonna force, I guess let's do k plus 2. So this is 7 characters long. So we force the last 6 characters to be a 1, and then the character before that has to be a 0. Yeah, does that answer your question?
Yeah, I think so.
Okay. So, where was I? Yeah, I think that's pretty much it for this.
Submit.
I still can't quite submit because there's another variation you have to account for.
Oh.
So, okay, now
Submit anyways.
let's try to solve this problem where you can have no more than A 1s in a row and no more than B 0s in a row. That, I'm not going to code this one. This one's a bit much, but
Do we pretty much just copy the transition for zeros into the transition, or sorry, the transition for ones into the transition for zeros, and use the 2 different parameters?
yeah, so it's something like that. It's exercise left it to the reader. That's like basically what this problem is. It's like you have the question marks and you have the you have condition on both and. Okay, go to the next problem.
By forcing that 1, 0 that you need, couldn't that mess up?
Oh, yeah, also that's, yeah, for that one you would have like another state, which is like what the last character was.
Okay.
That's what I did for that. Okay. Alright. B. Count the number of paths. You have a grid of H by W. Now count the number of paths from, some of the cells are blocked. Now count the number of paths from the top left to the bottom right corner such that you don't go through a block step. Grasp?
Inclusion-Exclusion.
Yeah!
Yeah!
Maybe not actually.
Well,
Yeah, something like
I
that.
mean, when I solved this problem, that was kind of what I did, like, based on, like, how many, like, different obstacles you hit, like, on the path, like, that decides whether, like, you're excluded. Like, it was, well, the DP transition was,
And it's 2000.
well, yeah, but I'm saying, like, you only consider the, like, the obstacles, and, like, you can get, like, the paths between them.
Well, okay. Tyler?
It's like your DP is going to be on, look, you sort your obstacles based off of, like, distance from the top left corner.
Okay.
Like sort by X's, break ties by Y's, or something like that. My brain's not logicking.
Both of them
But
would
yeah,
probably
but,
work.
then now we can do a DP on the index of the obstacle we're on. And then it's like, we look at all previous obstacles saying this is going to be like the last obstacle that blocked us. And we can say that, well, we start off by saying our DP answer is going to be the number of paths from the top left corner to the current obstacle we're looking at, which we can do using like stars and bars.
Okay.
And then we look at every previous obstacle and say, how many paths does this obstacle block from us? And subtract out those DP states.
Okay.
That's kind of what I was trying to explain, except significantly more complicated.
Alright. Where's that? Oh yeah. So that's pretty much the idea.
I feel like writing a little bit of pseudocode might be helpful for.
Yeah, can you explain it again, Andy?
Yeah, okay. So, what we're gonna do is we're gonna do a DP, which is like, for each obstacle, we wanna know the number of ways to get a path from the top left corner to this obstacle without hitting any other obstacles. And then we also will just like put an obstacle at the bottom corner. Jason?
Is at least one path guaranteed, or do we need to do like extreme cases and when n is?
Yeah, there's not necessarily a guaranteed path, but you are guaranteed that the top left and the bottom right are not filled.
Okay.
So we're gonna have a DP. You know what? You know what? How about this? Let's just start writing some code. That always helps.
ABC.
Always be code. So we have HWN, and then we have our obstacles. I forget if it's, I think it's one and next. Yeah, one and next. So I'm just gonna zero next it. So now, and we can just like sort these. So now we're gonna do a DP, which is,
Do you want to add a dummy one at the end or not?
yeah, you're right. We're also gonna add another obstacle for the bottom right corner. Because our DP is like based on, it's kind of weird because our DP is like we want to hit the obstacles, but we want to hit like exactly one obstacle in our DP. Nick?
X is presumably a horizontal coordinate. Are you using X as a?
X is the row, or, yeah.
Oh.
As long as
Doesn't
you're
really
consistent.
matter.
Yeah, I mean, it matters if the next slide is.
Oh, yeah.
Alright.
N plus one.
No, because I already have one for the
last guy, yeah.
the last guy. So,
Wait, but the
Okay.
input doesn't give you N plus one though.
Oh, yeah, because N's not
you're right,
adjusted.
right.
Getting gas.
So that's N plus one. You know what? Let me actually just draw some stuff out so it's easier so I can see. So we have some obstacles like here, here. So our DP is going to be like for each obstacle, we want to count the number of paths to this obstacle. So for example, for this obstacle, we can like count this path, like something like that. All the paths to this obstacle that don't hit any other obstacle. So then for this obstacle, we could like have this path, this path, this path, but then we wouldn't want to count this path because it goes through that obstacle, right? Does that make sense, everybody, for like what we're trying to compute here and how that like, and then and that's why we add another obstacle to here because that's just this. So how do we compute this actually? Yeah, any ideas on how to compute this?
Would you start at the top leftmost obstacle and compute all the paths that go to it?
Okay.
And then ignore those paths when computing the next obstacle?
What do you mean? How do you ignore the other? How do you ignore those paths?
So you would take like the next obstacle and find all the paths that would go to it and just subtract by the amount of paths that came from the block before it?
Yeah. So
Not just the block before it.
The block, so the blocks before it.
Yeah, you also need to check if you can reach another obstacle from there, like, avoid like subtracting more. If you have two obstacles that are like the same distance, you cannot go from here to here, so like, you cannot subtract this.
You also have to, so you're saying like you have to check to see whether the obstacles can reach each other?
Exactly.
Yeah, okay.
I was gonna basically say like, for a guy, for any guy, like for an obstacle, for anything in its like envelope, like a corner before it, for any of those, we've already computed the actual number of ways to get there. If from that element, from that guy, if like the space between us is completely clear, then we're gonna subtract out the actual number of ways to get to that guy that we're subtracting out times like the like choose formula for like this clear spot, and since that's only going to consider like the kind of the convex like thing of guys that like actually matter.
Okay, so you're very close there, but okay. So let me go explain what you're saying. Clear. So you're saying like for each guy, you count the number of paths, like assuming like this area was clear, you count the number of paths from the top left to this point? Is that what you said?
I'm saying like assume that for this guy, all of the ones in the corner, we've already computed their DP of
Okay,
like
so
the actual number of ways to get there. Like,
so everything here is already computed?
yeah, so like that corner guy, like we're like only including the paths that like don't go through 2 blocked obstacles, right? Like, or don't go through the blocked obstacles, right? And then now to use those, we have the actual number of ways of getting there, and we're saying like this area between us is clear. Like we're only gonna end up subtracting out the ones that like matter, because you don't want to double count like you don't want to count like the paths that are blocked.
Blocked by 2 things?
Yeah, you're only gonna like subtract it out when it's blocked by like the kind of closest guy that you've computed for real.
So are you saying like if you have a path like this, you would only like
you're gonna subtract out the number of ways to get to that like second stair, right? Times like the clear paths.
this one? Wait.
You have the DP that computes the actual number of ways to get to an obstacle.
Yes. Okay.
And then we're saying to get to that corner,
This corner?
yeah, we are subtracting out the number of ways to get to that.
Why don't you just number them, please?
Yeah, okay.
To get to that corner, we are subtracting out the actual number of ways to get to 3 times like distance plus distance choose, like, you know what I mean, the clear formula. We would not do anything for 2 because there's something in between.
Ooh,
No?
no, that's not quite. Tyler?
So, like, let's say we're computing the answer for 5 right now. We go through every previous index. And so, like, let's say we're looking at 3. We can subtract from our answer. Well, we start off by assuming everything's clear to get our initial answer. And then when we loop through each of the previous indexes, let's say we're on 3, to find the number of invalid paths that are caused by 3, we can then use the choose formula to find the number of paths between 3 and 5.
Yeah.
And this just works even if there's an object in the middle of us, because if we look at like 2, 3, and 5, for instance, all of the paths that go through 2, 3, and 5, 3's DP will exclude already. So the only invalid paths are going to go from, or the only invalid paths we need to consider are those starting at 2.
Yeah, okay.
Well, not only considering those, but like for this current transition, I mean.
Yeah. So it's like every path is going to be like every path. Okay, so you have some path that goes through some set of obstacles. Like this path is only going to be counted by the first obstacle. That like this path is only going to exist in the first obstacle's DP value. Like if you have this path again, this path is counted for 2 but not for 3. So like it kind of just works, right? Like if you subtract out, okay, let's say you only subtracted out from 3's DP value, you wouldn't subtract out this path because 3 doesn't count this path. You would have to subtract out from 2 as well because 2 is the first. We're like subtracting out the first, like we're using the first obstacle on the path to subtract out its value. Also, before I just want to make sure, does anybody want me to go over like how to get the answer for an empty, like a completely empty grid? Is that necessary? Okay, cool.
Are we only going down and right, or is it any path? Like,
Yeah, down and right.
Oh.
Like if you could go up and left, like.
Yes, that's a lot.
That's technically the infinite. Like it's simple paths, isn't number of simple paths in a graph NP complete?
Yeah, I think so.
Yeah.
All right. Let's get coding. So, let me just like add a function here for like counts with empty.
Do we need to code this one?
I mean, it's like really short. Don't worry about it. So, So now it's like if you had it's just like the blocks that are typed.
Line 48, shouldn't it be x plus 1, y plus 1? Because it's 0 indexed.
Yeah, sure.
Because it's based off number of rows and number of columns.
Yeah, you're right, probably. Okay. And I would just do like. Alright, that's like it. Any questions, comments, concerns?
I'm assuming this would probably be under mod.
Yeah. More. That's. Give it a moment, just,
I don't think it's actually x plus 1, y plus 1.
What?
I think it is just x and y.
Well, it depends on what this function does.
I'm assuming this function does stars of ours.
You could say that.
Alright.
This function
Okay,
is
yeah, it does depend on the functions.
like it's fun.
If the function is just like h plus w, choose w, then you don't want to have the plus ones.
But it's not. The function is just like okay. This function specifically is to solve the problem if there are no obstacles using the same h
Well, I
plus
mean,
w.
it is just h plus w, choose w.
No, it's h minus 1 plus w minus 1 choose w.
Oh,
H
true.
minus 1.
Yeah, because this is saying count the number of ways for an h by w grid.
Let me just
Well,
read
yeah,
this.
but yeah, you don't need the minus one to the function call though, because like it will be height minus 1. Subtract that, so my value.
Wait, why is that minus 2?
It's like h minus 1 plus w minus 1.
Because again, this is solving for a grid of h,
Also-
height h.
Yeah,
What's
so,
W?
so like that's what I
Oh,
was
you need
saying
the-
though, like
You need the
you're
plus
doing,
ones and, no, you need the plus ones in that case.
you're doing the minus ones there, but you're like plus oneing in the input, so you could just like not put it in. You don't.
But it's taking in height and width, so it's taking in number of rows, number of columns.
I think we can stop talking about this.
Alright, let's go to the next problem. Alright, I'm not sure, okay. This is a CSUS problem. How many of you have this problem? Raise your hand if you've done this problem. Alright, cool. So,
Oh, this is a good one.
yeah, just let me read it. You have k distinct primes. You want to count the number of numbers less than or equal to n that are divisible by at least one of these primes. Yeah. Any ideas?
It's Mogan time.
No.
No, oh, am I thinking of a different one? Oh, I'm thinking counting
Bro
rows
did
by
not
grid.
make a problem.
I slammed the bit mask inclusion-exclusion.
Okay, you could do that. Let's not do that though. Let's not do that. That's a thing.
DP.
DP. Okay. What is your DP? Okay. Based on what you've seen so far, could you extrapolate a DP for this? Session?
Maybe your DP is like your state is, like for a given x, DP of x is the number of the first n positive integers that are divisible or not divisible by x, or that's not right. Divisible by x, but not divisible by any of its divisors.
What?
Sorry, that's not right.
Okay. You're given 20 times.
I'm gonna extrapolate that the state is gonna be the length of the prefix of the input array that we're considering.
Well, you probably would be wrong about that.
Oh.
So I would say, Tyler.
Our DP is the mask of primes we're divisible by.
Okay. Jason, do you have something?
I was going to say something where we're inverting the at least one, and it has to do with the k primes.
At least one. Okay.
Like inverting that, so none of.
Yeah. So that's a good point. So what we want to solve is like another. Okay, let's invert this. Let's try to solve like the number of ways to get exactly 0 of the primes, and then just subtract that from that. Because like Oh yeah, it's very easy to count the number of ways to, like, the number of how many numbers are there that are divisible by some subset of primes, like every prime in the subset? How would you do that? Like I give you some set of primes, I want you to find the number of numbers that are divisible by every prime in the subset. I guess.
Multiply them all together, divide.
So you do like n divided by n products. That will work. So now like I don't know if you like, could you see some sort of analogy with this? Like it's pretty easy to find the paths to a node. So yeah, okay, Hector.
I wouldn't know the math, but like, my idea would be like the DP of how many these numbers are only divisible by this prime, and not the others.
Like one prime?
Yeah, like, well, first start with the first prime.
Okay.
How many numbers are divisible by in the whole range? When I get to the second one, I get like how many numbers are divisible by the primes before, and I like compute like, for example, if I have 2 and 3, I compute how many are divisible by 6
Okay.
of those primes, of those numbers before the DP before. The point is like the DP can only stores how many numbers are like only divisible by this prime, but not the ones before. What? And it's trying to see how many match. I wouldn't know how to do the math.
Okay, yeah, that's like that's an idea. Not quite what we're going for though. I think it's like kind of similar to that. But what we like, the thing is, we want to like do something with, I don't know if you're saying.
Yes, it's the same idea then.
Yeah, but we want to do something with bit masks though, right? Because it's like, we want to do something here. We can't really do things on a prefix. I haven't really thought about this, but like, you can't really do things on a prefix because you still have to consider like the numbers after you and like how they stick together. I don't know, Jason.
So for the bit mask, would it be of length k referring to whether we're divisible by each one, or?
Sorry, what's that?
You were referring that we're trying to use a bit mask for this, right?
Yeah.
So would it be of length k where each bit determines whether we're divisible by the ith one?
Yeah. So, okay, you know what? Let's get coding. So I'll get my k and k. I think it's k.
It needs to be a long.
That's fine. And then we'll be like, oh, that's k. So now we want to do some sort of DP on bit masks. So we're gonna have 2 to the k gains. And like, we could do something, okay, what I'm trying to get out of here is we want to do something similar to this idea where we like get some, we want to subtract out all the ways we can get from a bigger bit mask to like this guy. I don't know, let's get coding and see if you can like figure something out. This is mask. And then, let's say dp of mask is equal to n, and then we need to like, also for, what you were saying about taking the products, like, the product can get pretty, I ran into this issue, the product can get really big for this, so like you have to like, do the divisions as you're,
For loop thread.
yeah. Alright, is anybody confused by that?
Can you elaborate on what exactly the transition is doing?
There's no transition.
It's not a
yet.
transition yet.
This, like, I'm not done yet. So, now we want to do, I don't actually know.
Oh, I see.
I haven't actually, like, I don't actually know quite how to do this. Just imagine I can somehow get, like, super masks and mask. And then we're gonna be like, how does that sound?
Isn't getting all super masks 30 to the end?
Yes.
Then that's gonna be kind of bad for n equals 20.
Yeah, we're gonna do something better later.
Is it gonna be some more subset?
Yeah. Alright, alright, alright. So okay. So like, I guess I don't know, what is this doing? Does anybody know what this is doing? I'll start with that. So, what?
It's like finding the number of numbers that are divisible by this like mask, but not any like larger masks.
Yeah.
It's like super masks.
So, that's actually, that's exactly what's going on. We're subtracting out, okay, so for our DP, we've already computed the answer for all of our super masks. So like, we know for all of our, okay. Okay. Let me actually clarify one more time what this, like, this is actually what the DP is doing this time. The DP is going to store for each mask the number of numbers that are divisible by exactly this mask, nothing more. I mean, it could be something less because of course you're always divisible by all of your submasks as well. The DP stores for every mask the number of numbers that are divisible by like exactly all of the primes in this mask, and no other primes is it divisible by. Like no other primes that we care about at least. So so what this is gonna do, so this is like a good approximation. What this is trying to do is it's trying to like figure out the number of, this will tell you the number of numbers that are divisible by at least this set of primes. But the problem is this could give you like some other primes that you're also divisible by but aren't in the mask. So then what we do is we go over all super masks of this mask, and then we subtract out like the number of ways, because we just like don't want to count those guys, right? So yeah.
Isn't this hella slow?
Yes.
Oh.
Gonna make it faster. But does that seem reasonable? Okay. How do we speed this up? Well, I'll just tell you how to speed it up, and you can like think about why this works. How many of you guys have seen sum over subsets? Okay. So we're gonna do a little bit of sum over subsets. Actually, let me just like tell you about this. So if you notice something very interesting here. Wait, did I do that? Right? Okay, whatever. This value over here is like gonna be the sum. The value of DP mask here is going to be the sum over all supermasks of the like resulting DP value. Like the DP value at the beginning is going to be the sum of the DP values at the end over all of your supermasks. Because like you just like I mean it's like obvious. Yeah. So like that's where the sum over subsets comes in, but that's not a big deal.
So now you're trying to like undo that process.
Yeah, something like that. I forgot to get rid of this. And then I think it's, yeah. How does that seem? Does this code seem familiar to people? What does this look like? Well, suppose it should look like sum over subsets if you've seen it before. But it's like invert. You just like invert it, right? I don't really have time to go over why this works, but just hope that it does. So this does the exact same thing as before, as like the going over all supermasks, but it does it like in parallel kinda. But the end result is going to be the same.
I think specifically, you should say that it's like inverts sum over supersets, not subsets.
Yeah, this one sum over supersets. Like if you wanted sum over subsets, you would just flip this thing. Let's run it. Just to be convincing. Seems right. Let me submit it. Actually, I won't submit it. That's a lot of work.
Just
So,
define it log on.
you're right. Yeah, that probably compiles.
Yay!
Alright, how do people feel about this problem? Like, raise your hand high if you feel very confident, and then like lower it as the less confident you are.
About like how you understood.
Yeah. How good do you think you could get this problem? Alright, that's pretty good. Let's do, how much time do we have?
Make it
5 minutes or so.
Alright, let's speed run this one, okay. GCD competition.
5 minutes.
I'll let you read it. I can't really like explain it much better than this. Tyler?
Is it Moban time?
No.
No, it's never
It's
open
never
time.
open time.
See, this lecture is not about inclusion-exclusion or Mobius or anything.
Is it Mobius adjacent?
Yeah.
It's
Okay.
like a superset of
If I wanted to use Mobius, could I
You
use
could.
Mobius to solve this?
Mobius online using.
Oh.
Alright. I'm assuming you've all understood this. So, like, we can just do this exact same thing we've been doing all this time. So, okay, first of all, how could we solve this problem just for a single GCD? Like, if we want to solve this problem, we have let's consider some K. How many ways can we do it to, like, get the GCD to be a multiple of K? How do you solve that? Like, we want to get this answer where instead of GCD of ij equals K, GCD of ij is a multiple of K. Is divisible by K. Yes? No? Yes? Sachin?
For all multiples of k, you like sum those indices of a and b, and then multiply those two sums together.
Okay, yeah, that's exactly what we're gonna do here. So, let's go, gotta go fast.
Are you want indexing for implementation details?
Yeah. Alright. How do you guys feel about that? Do you agree that this solves what I said it would solve? Alright. So now we can go ahead and do the same thing we've been doing, where we want to, like, now we have this answer, but now we need to subtract out all the answers for, like, assuming we could get the answer for everything that's a multiple. Okay, the problem is this doesn't solve the problem because the GCD can be a multiple of K. But like, assuming we've already solved the problem for the cases where the GCD is a multiple of K, like if we solve the problem going backwards in terms of K, like bigger K to small K, Brian?
Is it harmonic sums?
Yeah, I mean that's what this is. Also, yeah, the red time of this is unlocked now, just for fun. So if we go backwards, then we can just, like, if we have the answer for all the cases where the GCD of K is like a strict multiple, if the GCD is a strict multiple of K, then we can just, like, this tells us the number of ways that the GCD is a multiple of K. So we can just, like, subtract that out. So actually, let's do that. Let's just go backwards. now you can just go like, you can just do like.
You mean J plus
Plus equals
I.
K.
Oh, yeah. Yeah. How about that? Let me think this up. Samples. Seems about right. Split. This is under mod.
He's been doing this a while.
Did not know you could do it like that.
It still runs.
Is it multiplying? Multiplying summing is gonna be, that's actually.
Yeah,
Oh,
I have never actually submitted on this, so hopefully this works.
You're gonna have to wait like
Make it
2
a one.
minutes, 2 or 3 minutes for a
Really?
response.
Is it that
Wait
slow?
for.
Oh, okay. Well,
What's WJ?
It's probably waiting judgment.
Oh.
AC.
AC apostrophe.
it's a long compile.
Compile time error?
Oh, one case.
All zeros. Let's go.
All zero.
This is so slow.
He wins.
Let's go do this. How long segment?
You got samples, it's easy.
We're still the small.
Proof by 7 cases.
Well, it has to be 8 cases, but we already have 9 cases.
Okay, surely this just ACs all the
We
way.
gotta get to a large case and then.
Yeah.
It's only small
it's only
cases.
small cases.
I don't know, 1 millisecond.
Oh my god, how many small cases are there?
The is code's correct.
What? Where did the new.
Okay, now go up. Now it's doing medium. It's like doing medium.
Random. Oh, we're on random.
What? Oh no.
Max random.
random.
Okay.
Okay, this just ACs.
Okay, yeah, that is.
Six.
Surely.
Near prime.
Okay, there's only 5 more cases left.
Proof by 25 cases.
Find ACs on
All
also
the
do
cases.
Two.